What is HMM? A hidden Markov model is a statistical model used to model sequences of observable events that are assumed to depend on some underlying unobservable states. It was proposed by Bond L.E. and his friend Pretry in 1966. Why HMM? Since the 1980s, HMM has been successfully used for speech recognition, character recognition, and mobile communication techniques. How it works? Well, the HMM is a type of Markov chain. Its state cannot be directly observed but can be identified by observing the vector series. It had a serious impact on mobile communications after the 1980s. Why hidden? It's called hidden because the states are not directly observable, but the sequence of observable events can provide information about these hidden states. Where is it used? HMMs are widely used in various fields of communication, including speech recognition, bioinformatics, natural language processing, and many more. What are the components of HMM? There are 4 components, namely hidden states, where they are underlying states of the system that we cannot directly observe, transition probabilities that represent the probabilities of transitioning from one hidden state to another, observations which can be directly observed that are events or data points, emission probabilities. These are the probabilities of observing a particular event given the current hidden state. Let's understand it through an example. Let's consider a simple example of weather forecasting where we have 2 hidden states representing the weather conditions. Let them be sunny and rainy, represented by S and R respectively. We observe 2 types of events, walk and shop, represented by W and S respectively. Our goal is to predict the sequence of hidden states, that is the weather conditions, given a sequence of observations, that is the activities here. To solve this problem, first we'll initialize them. Start with initial probabilities for each hidden state. For simplicity, let's assume an equal chance of starting in either state. Then we'll calculate forward algorithm. Calculate the probabilities of being in each hidden state of each time step given the observed sequence. Later on, we'll continue calculating the backward algorithm. Calculate the probabilities of observing the remaining sequence of events given each hidden state at each time. Then we use forward and backward algorithm and decode the sequence of hidden states. Let's understand how they are implemented. In this collab file, I've already pre-coded the HMM program. Let's understand what I've done here. We are first importing NumPy for numerical operations. Later, we are going to define transition matrix, here represented by Tm, and initial probabilities represented by IP. Later, alpha, representing the forward algorithm, is initialized with shape of length of observed sequence OS and length of initial probabilities IP. We'll compute the forward alpha and using for loop, each time step t, iterate over each hidden state j, compute the forward probability for the current state and time using the emission probability, the sum of the previous forward probabilities weighted by transition probabilities and the current emission. Store the computer forward probabilities in the alpha array itself. Later on, we'll print them. The printing the probability of the observed sequence computed using the forward algorithm determines the most likely sequence of hidden state corresponding to the observed sequence. Let's run them. So, we finally implemented hidden Markov model. Thank you.